Okay. Okay. We're recording now. That's good. Uh, okay, Jim, we'll turn it over to you. So you've got the screen.
Thanks, Wilton. I appreciate your inviting me to talk to you today. Jim Farmer, K4 BSE, retired electrical engineer, retired and useless. But then some people say I've always been useless. As you're probably aware, Wilton and I know each other because we share a couple of fantastic grandchildren, Thomas and Elizabeth. And oh yeah, their Mama Susan and their Daddy Kyle are my daughter and Wilton's son, respectively. And it was very neat that one of my daughters married somebody whose father was in the ham radio too. So that's great. That's not the only serendipitous thing that has happened to me in recent years. Just last year, we moved to Fayetteville to be close to them. And we had been up and coming on the north side of Atlanta. And we were looking at different houses down here when we were thinking of moving. And we got to this one particular house, and I was walking through one of the bedrooms and happened to see on a little desk on it an ARRL logo sticker, just a real small one. Nobody else would have noticed it, but of course I noticed that right first thing and said, wonder if they had somebody who was in the ham radio, maybe one of their sons. Walked downstairs and walked into a big room down there, and there one end of the room was a bunch of radios. Walked out in the backyard, and there were a couple of antennas. And I said, hey, this is my new house. And so sure enough, the people that lived here before us were both hams, both active in the club here. And so it's a small world sometimes. Anyway, the topic this morning is, I called it a practical tour through the world of FM. Be talking about FM, a lot of it oriented toward repeaters, but not all of it. And anytime you want to ask a question, I prefer you just yell out then and say, hey, stupid, stop and answer my question. If it's something I'm planning to come to anyway, I'll tell you, and we'll make sure I come to it.
And Jim, I have everyone muted, so if you'd like to do that, unmute yourself. Before I was hearing a little background noise, so I went through and muted everyone. So if you'd like to ask a question, unmute yourself first. Okay,
thanks, Greg. Good point. Yeah. Yes, just unmute yourself and ask the question. I can't see everyone on the screen, and besides, I get carried away listening to myself. Nobody else likes to, but I like to listen to myself. And I may not see a hand anyway, so just yell it out. Okay, I'm going to mix up the order of slides slightly from what I sent out. The slides are the same, just I changed my mind on the order of slides. Let's first talk about what FM is, and this is some of these first few slides are going to be some of the little technical that we really talk about this morning, but bear with no man for a few minutes if you would. What is FM? Well, let's start with any radio signal. Well, first, any engineers and technical hams like to draw pictures. And the main kind of picture we like to draw is graphs. The main graph we're going to be talking about, although we will hit one other, is one that is plotting time on the horizontal axis and amplitude on the vertical axis. If I have a signal that is represented by a voltage, and that signal is positive, then I will go up from the median or zero or reference level, which here's been raised just to make it clearer to see. I will go up positive from that. If it's a negative signal, I'll go down from that. So this is a basic sine wave, the basic wave shape of any electrical signal, although we'll modify that as we'll see shortly. Now, the only difference between say an audio frequency signal and an RF signal is the frequency. as the frequency for the same time scale plotting, then as I go up in frequency, I'll have more of these cycles per unit of time. So the more cycles, the higher the frequency. As I go way up in frequency, even more than this is illustrated because we just had to keep it down to something that you could see in an illustration, then a higher frequency would look like this. Well, a higher frequency, just a sine wave, nobody cares about that. It's not interesting. We want to transmit some intelligence on this signal. In order to transmit some intelligence on it, we have to change it or modulate it in some way. Modulation simply means a change. And there are basically two ways I can change this signal and put intelligence on it. Well, sometimes what's put on it, it may not be intelligence, but and that's another issue. I can change the amplitude or the height of the signal, and that's called amplitude modulation, or I can change its frequency or frequency modulation. Now, when we talk about UHF and VHF for good and proper reasons, we normally, but not exclusively, talk about frequency modulation. I can represent frequency modulation by when the frequency goes up. I show these squiggles representing the cycles of the signal closer together. And when the frequency goes down, I show them separated more, spread out more. So what I will do in order to put intelligence like a voice signal on the carrier, I'll frequency modulate it. Let this be the voice signal, which is more complicated than just a sine wave, but this is the easiest signal to represent things with. When the amplitude of the signal goes up, then the frequency will bunch together. When it goes down, the frequency will be separated. This happens at the audio modulation rate of generally between about, for communications purposes, between a couple of hundred hertz and about 3 or 4 kilohertz. For entertainment and music applications, it'll be a higher range, but that's not what we're talking about here. So just a few kilohertz of, or even less, of frequency is modulated on something 146 megahertz or so. This carrier is what we refer to as the frequency of the signal. Here's another way of looking at the same thing. Here's my amplitude versus time graph again, just like you saw before in the same sine wave representation of the audio signal. Here's a different picture on top, a different graph. This one plots frequency versus amplitude. The time is just represented on here by where the frequency is at any given point. When the frequency, or excuse me, when the modulating signal goes through 0 or the midpoint of the signal, and it's not 0 on here, but again, it's off shifted to make it easier to see. But when we go through the midpoint of the signal, then we're at the actual carrier frequency, the F or transmitted frequency, the center frequency. That's the frequency. When we refer to the frequency of a repeat or something, that's what we're talking about, is that frequency. When the signal goes up, for example, then the signal will scoot over to a higher frequency. And the modulating signal goes down, the signal scoots over to a lower frequency and back again. So I've got this frequency going up and down all the time, according to, in our case, the audio modulation. So the frequency is moving at an audio rate. I apologize for getting off there. The amount that the frequency goes up or down is called the peak deviation, or just the deviation. We represent that by a delta F. So if the carrier frequency is F, and we go up to a delta F positive or a delta F negative on the respective positive and negative peaks of the signal. Hold that idea of peak deviation because we're going to refer to that again in just a few minutes. This is a basic block diagram of a FM transmitter, such as you'd have in an HT or any other FM transmitter. Microphone through what audio amplification is necessary to a IF oscillator or local oscillator. Excuse me, let me just call this an IF oscillator, not local oscillator. That has a different meaning. Now, this is a particular a particular type of oscillator called a Varactor controlled. A Varactor is a type of diode that when reverse biased has a lot of capacitance between the two terminals, and that capacitance is proportional to the voltage on that diode. So by doing that, as we put the voltage from the microphone across the Veracter diode, it changes its capacitance. It's in an oscillator circuit such that it changes the frequency of oscillation of the oscillator. And that goes through a bandpass filter, is mixed up with a local oscillator. That's why I didn't want to call this the LO. A local oscillator, which is a BFO usually. This is what you're adjusting when you adjust the frequency of your transmitter. To the output frequency, more bandpass filtering, more RF amplification, typically more bandpass filtering, and out to the antenna. So that's what an FM transmitter looks like, and an FM receiver is kind of the opposite thing, with the Veracter controlled IF oscillator usually being replaced by a discriminator, a particular circuit that can put out different voltage depending on what the frequency is. So let's talk for a minute about the peak deviations. Remember, I talked about peak deviation, and it's different for different services, and there's a standard that we follow. The standard we normally follow for amateur and commercial voice is 5 kilohertz. So this delta F, the deviation from the center frequency to the either maximum or minimum frequency we scoot to, is 5 kilohertz for our purposes. Now, sometimes FM uses 2.5 kilohertz for narrow channels, and there was a higher deviation standard in use at one time that's now pretty much obsolete. Back when we had analog TVs, the standard for the deviation of the sound carrier, which was FM, was 25 kilohertz in the US and 50 kilohertz in Europe. For FM radio, the standard is 75 kilohertz. Why more deviation? More deviation gives you more signal. The louder, or the more deviation you have, the louder the signal sounds, all else being the same. So why don't we want it louder than some standard? Because when your radio is set up to work with some standard, if you go much over that, you're going to get distortion. And obviously, the more deviation you have, the more bandwidth you're taking up, and the fewer stations can occupy the same bandwidth. But you get better signal to noise ratio, or something related to that called SINAD. SINAD is something used by FM communicators. It's a measurement of the quality of the signal as far as distortion and noise goes. It stands for signal and noise and distortion. So SINAD is the ratio of signal plus noise plus distortion to simply the noise and the distortion components. We sometimes call that, since noise is what you get from random motion of electrons and amplifiers, and also just because of temperature in an antenna or something else. Distortion is something we do to screw up the signal in the transmitter or the receiver. And usually here we're worried about the receiver more than the transmitter, but that's neither here nor there. Both of those, noise and distortion, are just garbage. So we sometimes call it the signal plus garbage to garbage ratio. So I've said that the higher the distortion, the louder the signal sounds. Well, and we're supposed to be distorting 5 kilohertz. Well, in amateur service, how close do we come to those 5 kilohertz? I did a little experiment one time back when I lived up in Forsyth County, Cumming, on the top side of Atlanta. On our ARES net one night, I set up so that I could measure relative distortion. I couldn't measure absolute distortion. I wasn't set up, absolute deviation. I wasn't set up to do that, but it's pretty easy to measure relative deviation. So that's what I was measuring here. I'll talk about how to make an absolute measurement later. So I looked at the quietest signal of anybody responding to the net that night and the loudest signal, and plotted a bar graph of all the 24 participants that night in between. And this is what I got, a 20 dB range of signal level. Now, dB is a way we talk about ratios of two numbers, in this case, deviation range. And that also is equivalent to the amplitude or the signal level we hear, the volume we hear. How much is 20 dB range? That's a lot when you're dealing with communications radio. That may be all the signal to noise ratio you have if you're in a car with a lot of other noise. So if I were to set the highest signal level to be a comfortable level coming out of my receiver, at lowest signal level, I would hardly be able to hear that. Vice versa, if I set this to where I could hear it comfortably, that would blast me out of the room. Well, lest you think that the people in Forsyth County are worse than other people, when I came down here to Fayette County, I did the same thing one night on their net. And of the 15 people on the net that night, that's the reason these bars are wider, is because there were fewer people, so the software had to put in fewer bars. The quietest to the loudest, guess what? Essentially the same thing, 22 dB range. That's not good. So what should we be shooting for in deviation range in our HT in FM? Well, this is kind of my opinion, and you'll find people who disagree with this opinion. I think a 6 dB variation from one station to another is probably pretty outstanding, but it's probably not something that, as a practical matter, we're going to obtain. Now, FM radio stations come a lot closer than that, but they have a lot of expensive equipment they use to do it that we don't have. 12 dB I would consider bad. So something like between 6 dB and 12 dB I would think is probably what we can realistically expect, although I would like to see something lower. But the ugly is 20 dB variation, which I measured on both of those nets. It's almost impossible to receive when you're mobile, because you'll set for a comfortable volume on the loudest station. The softest station comes out, you can hardly hear them. It's even difficult to tolerate when you're in a fixed station. So how do we ensure consistent deviation on our radios? Well, we got to go back to the deviation standard. That's why we have it. So if everyone hit exactly 5 kilohertz, everyone would sound equally loud. And I should say that loudness is more complex than what I'm making it out to be here. So how do you know when you're deviating 5 kilohertz? When you talk on your radio, you ask Brian to measure it. Who's Brian? That was W3CP. He was a member of our club up in Cumming and a very sophisticated engineer. He had all of the equipment to make measurements of deviation on a transmitter. Here I did talk about, again, I mentioned earlier that there used to be another deviation standard, 15 kilohertz, and that's pretty much gone away now. But the problem is we don't have Brian here. I don't have him down here. I wish I did, but I don't have him. So how do you maintain 5 kilohertz when Brian is not around with his neat professional gear? And we had him bring the gear to a club meeting one night. And as I talked about this, people could bring their HTs up and he would measure them. And he could give them a report of what their HT was, how it was performing, including deviation and some other things. So I told people there, you just try to remember what you did when he was around, and he got you deviating about the right amount. Now, the repeater we had up there, WB4GQX, the voice announcements on it were set pretty carefully to 4 to 4.5 kilohertz deviation. So you did have a reference on that. You knew that when you heard the voice announcement from the repeater, that it was deviating 4 to 4.5 kilohertz. And I can tell you, nobody sounded that loud. So nobody that I measured was coming anywhere close to the proper deviation. But unfortunately, we don't all have that around our repeater here. I asked the guys who maintain it, and they weren't sure what the deviation was. They only have a CW identifier here, and they weren't sure what the deviation was on it. So we lost that. We're working on a way with simple ham equipment to try to get you where you can measure that. And I think we've got a way that one of my friends here suggested. I need to try and make sure it works. In order to read the deviation and get the dB numbers that I did, there's a audio capture program, a free program you can get called Audacity. And it's used for audio capture for recording. In fact, a lot of professionals use it for recording, and they like it because it's free. And it's a pretty credible recording and editing, audio editing program. And it is free, did I mention that? But it has VU meters, volume unit meters. You've heard of VU meters before, may have seen some. And this is what we call the meters that we use to measure volume units. And so you simply use your computer's microphone positioned close to your loudspeaker, and you can read that. In fact, that is the way I got these measurements back here. I simply used Audacity, and actually I captured it, and I went back later and looked to be sure I had the right audio reading, but that's the way I got it. This is a screenshot of one way Audacity can set up, and it can set up a lot of different ways. It has VU meters to measure playback level and VU meters to measure record level. So that's a good way to look at deviation. Now remember, this does not give you an absolute deviation. All you can do with this is look at relative deviation, one signal relative to another. So what tools can you use to adjust the deviation of your transmitter? Well, unfortunately, you don't have a whole lot of tools. You can speak louder or softer. You can move closer or further from the microphone. And a very few amateur transceivers have a deviation adjustment in the menu tree somewhere. Good luck on finding it. I found it on one of my radios one time, haven't found it again. Know where your microphone is on your radio and play to it. These are 3 different HTs that I have. And let me stop sharing for just 1 second here. Play to the microphone means make sure that you have your mouth positioned correctly next to the microphone when you are talking on it. I like to speak across the radio like this, not directly into the radio like this. Why is that? Because in English, some of our sounds are what we call plosives. What's a plosive? Put your hand in front of your mouth, pronounce a B or a P, B or P, and you'll feel air hitting your hand. That's because of the way those sounds are formed. B and P and several other things kind of have that characteristic. And that wind that you feel hitting your mouth makes a very distracting extraneous sound when it hits a microphone. You'll even hear this occasionally on broadcast radio. WSB here used to be very bad about it. They seem to have gotten that under control recently. So to prevent that, I like to speak across the microphone like this and have it maybe 2 to 4 inches from your mouth, something like that. So where is the microphone in your radio? Well, this cheap Baofeng I've got here has a little hole here, and it even is labeled mic. So I know where the microphone is on it. Here's a nice, expensive, fancy, do a lot of things Kenwood. Where's the microphone on it? Who knows? Who knows? It's not labeled anywhere on here. There's a little up arrow that might be it, but that's the best thing I can think of, is that maybe that up arrow right there is it. I hope. Here's a older HT that I had at one time. It's not working anymore, so it hasn't come out of the box since I moved down here. The manual implied it's about here, but nothing really to indicate it. On any of these, does the manual give you any real information about that microphone? No, it doesn't say a thing about the microphone, just assumes you know it. And some other microphones, such as on a desktop or mobile rig, there's a little hole. Here's microphones for 2 different mobile rigs that I had, and they each had a little hole. I guess that's the microphone. Now, I don't know that, because guess what the manual said about it? Not one word, but that's what I'm thinking it probably is. Now, one thing I couldn't find, because the only one I had worked so badly, I tossed it. The little add-on speaker mics you can get for HTs, I'm told that those things are notorious for not aligning the microphone behind the hole. That'll make the deviation low and can muffle the sound. So if you use one of those, you might want to check that out by having somebody listen to your signal and make sure that it's okay. So speak to the microphone. That should be obvious, but I've seen people who don't do that. Don't block the microphone with your cheek, hand, or any other part of the body, and I have seen that done too. Here's the microphone right here on this Baofeng. Seen people talk like this, with it actually up, with their cheek blocking it. Nope, that doesn't work. That muffles it. Hold it in front of your face by a couple of inches so that you don't do that. Don't block the microphone with clothing or anything else that's in the way. And as I said, it's best to speak across the microphone, not at it, to reduce plosives. And please speak up, don't be shy. I've seen some people really get shy when they get on the radio, and they hardly talk. If you couldn't hear me, I said they really get shy when they get on the radio and they can hardly talk. Speak up. I don't think that is going to cause you to over deviate in most cases. Okay, going to go in, if there are no questions at this point, going to go into some slightly more advanced topics now. So if you don't like more advanced stuff, take a nap if you haven't already gone to sleep. So what are some of the elements for successful communications at VHF, UHF? What are some things you need to think about? Well, we talk about receiver sensitivity and we talk about transmit power. Yeah, these do have an effect on successful communications, but other things I think can be more important. The antenna is extremely important. Anything is better than the rubber ducky that the device came with. So I have gone out and I have bought slightly bigger antennas. Yeah, they're more awkward a little bit, but they work a lot better than the rubber duck. This Kenwood that I bought several years ago, somebody had warned me that the stock antenna it comes with is particularly notorious for not being very good. So not too long after I got it, I walked into a ham radio outlet up here one day with the radio and held up the radio and said to the salesman, I need something better than this dummy load that this thing came with. He knew exactly what I was talking about. And he took me over and showed me some of his antennas. Sorry about that. A clear path between you and the repeater is essential, of course, because we're talking at VHF, UHF, pretty much line of sight. So the height of at least one is important. That's why repeaters are usually located, the antenna is located on the highest thing you can get on, a high tower or up in Cumming, we were lucky enough to have a mountain in about the middle of the county and a commercial radio station that was happy to host us on their tower. So we were in pretty good shape down here. We are on a county tower as high as we could get. Or deviation, as we talked about earlier, is important, but exceeding that standard will cause distortion. So you really want to hit the standard, not exceed it. Like I say, my experience is that most amateur rigs come under that distortion, that maximum modulation. That's the reason I tend, more than probably I should, I tend to talk pretty loud when I get on the radio, and probably to my detriment at times, but people don't care what I have to say anyway. Hi. So the closer you come to the 5 kilohertz, the better it is. Now, on another subject, as we get down in signal level, this graph, this picture, you got to look at a little bit differently. I'm plotting RF carrier to noise ratio this way. You can kind of look at this as signal level, although technically that's not correct. It's really the ratio of signal or carrier level to noise. And the audio synad or the signal to noise ratio on the vertical axis. Up here, we're talking about fantastic level of sound, pretty good level of sound here, scratchy down here until eventually the signal gets to be unreadable. And what this graph is doing is plotting what AM communications can do, FM communications, and digital communications. And don't try to compare these three. You can't do that. There are just too many variables that make it really impossible to compare. But all three of them, this is what they tend to do as you drop down in carrier to noise ratio, or like say, you can look at that as just carrier amplitude. With AM, you start out with a pretty good sounding signal. And as you drop lower and lower in carrier to noise ratio, you don't hear too much of a difference until you reach a certain threshold. And that threshold is really set up by your receiving and listening environment as to what that is. Then as you get below that threshold, you'll see your synad dropping off dB for dB with the carrier to noise ratio until it gradually just deteriorates to the point where you can't use it. FM, on the other hand, is going to have a little bit different look. The wider the deviation, the more pronounced this difference is. You won't hear much difference at all as you drop in carrier until you kind of reach what we call an FM threshold, which is lower than what you'd expect for AM. And then the signal starts dropping off gradually at first, picking up steam. And as the carrier gets to be less and lower, the signal really drops off really fast. FM kind of carries this to the extreme. Signal drops lower and lower and lower, and the digital sounds just as good, just as good, just as good, just as good, until all of a sudden, in a very, very short length of, or a very short distance, it drops off altogether. It just goes away completely. Now you say with the FM, wait a minute, I never hear it that scratchy or unreadable in my receiver. If it's scratchy into the repeater. Why do people say that? I'll tell you in a minute. But FM, we normally employ something called squelch. As the signal gets worse and worse and worse, at some point, and we're going to activate squelch. This is frequently adjustable somewhere on your radio, so that as the frequency, as the signal drops off in quality, at some point we activate squelch. You don't hear anything, it just turns off the speaker. And that's what typically happens in FM. That's why you may not hear too much of the noise. Otherwise, if you turn your squelch off sometime, and you'll hear constant noise. Well, you don't want to hear that. So that's one of the reasons we often use squelch. Although if you're doing weak signal work, obviously you wouldn't want to use squelch because you want to hear any little bit of signal that's there. Now, often on FM, you'll hear a little at the end of a transmission. We call that a squelch tail. That's a momentary burst of knowledge when the RF signal goes away quickly when somebody lets off on the mic, but it takes the squelch circuit a moment to realize that the signal is gone and to activate. And there's a reason for that. Now I talked earlier about the occupied bandwidth of the signal. How much frequency spectrum does this signal occupy? You might assume that it occupies from the carry frequency up to the deviation maximum and down to the deviation minimum. So the peak-to-peak deviation, you might think, is equal to the occupied bandwidth of the signal. Well, unfortunately, that's not so with FM. And this comes out of some higher mathematics of FM that I remember doing in college, but I couldn't do it now if you put a gun to my face. The occupied bandwidth is actually going to be wider than this. Now, the real equation says it goes on infinitely, but the signal level drops off to where who cares after a while. We can estimate the occupied bandwidth from Carson's rule, which says the occupied bandwidth is equal to twice the peak deviation plus the maximum audio frequency. The two comes from the fact that I'm using deviation, peak deviation, not peak to peak. So twice handles there to there, plus here to here, F to plus F, F to plus delta F, and F to minus delta F. That's the two. And then the peak deviation, which intuitively you might have thought was the occupied bandwidth, plus the maximum audio frequency. So for amateur use, the occupied bandwidth becomes 2 times, we said we used a peak deviation of 5 kilohertz, and we normally assume about a 3 kilohertz maximum maximum audio frequency that we're handling in voice work. So 5 and 3 is 8, 2 times that is 16 kilohertz. So we take that as the narrowest width of the filter we can use without distorting signal. But there's a caveat to this, or correction. We rarely deviate to 5 kilohertz with a 3 kilohertz sine wave. Most of the audio in most of our voices is carried at lower frequencies. So we can get away with a slightly lower bandwidth filter, and 15 kilohertz is usually the filter that you'll see. Now, of course, the filter it's not what we call a brick wall filter. It doesn't cut off immediately. There's some transition band in that filter. You try to make that as narrow as possible, or as minimum as possible for the transition bandwidth, but there's always some transition bandwidth. Usually when we talk about the bandwidth of the filter, we're talking about either 3 or 6 dB down bandwidth. Now, sometimes you will hear 2 stations. You'll hear this a lot on the FM band. When I was up and coming, on certain days, we would be listening to WABE out of Atlanta on 90.1 megahertz. And there was another FM station on the same frequency up in South Carolina, not that far away. And on certain days, if propagation was just right, I would actually hear WABE, the signal I was trying to listen to, would sometimes go away. And this other station would sometimes I would actually hear it replacing WABE's signal. And this is kind of the way that works when I have two stations. This is basically the signal to noise ratio versus synad plot you saw a few minutes ago. See that again. And as one signal is going up in strength to the right and the other station goes up in strength to the left. So here's station 2 going up in strength this way, station 1 going up in strength this way. I've kind of, I probably shouldn't call this signal to noise ratio. This is really just a quality of each signal, and don't read up or down into it, just read the level. If the one station is higher enough than the other station, then you only hear that station, that one station. So up here, if station 2 is higher in strength than station 1 by enough, then you're just going to hear station 2. If they're closer than that, then you're going to hear garble between the two stations. And this is probably worse than what I'd describe it as here. You're probably going to just hear garble. You're not going to understand either station. That's a function called something called the FM capture ratio, where it says that if one signal is larger than the other signal by a certain amount, then that larger signal is going to capture your radio, and you're not going to hear the other signal at all. And vice versa, if station 1 gets loud, gets stronger than station 2, I'm going to be down here and I'll hear station 1, not station 2. And in the middle, I'm going to just hear garbage. Here's a repeater block diagram. This is going to get us into some other stuff that we mentioned earlier. So this is basically what any repeater is at a very high level. Come in from the antenna through a receiver. Then we come out with baseband audio here. This is the same thing you'd normally put on a speaker. You combine that with local audio functions, which as a minimum is going to be a CW identifier to let you identify the repeater, and frequently will be audio identifiers. Maybe you'll have time and temperature announcements. Maybe you'll come off here to an auto patch, even though I haven't heard one of those used in decades. They still exist a lot of times. So local audio functions, whatever you have of those on your particular repeater. Then the signal goes back up to the transmitter and goes out the repeater output. And notice that the signal is remodulated onto a new carrier at the transmitter. So that and some other things say that the RF level you receive at your house, which comes out of this transmitter, has nothing to do with the RF level coming into the repeater. The signal output the signal level you get is going to be dependent on this transmitter and the path between this transmitter and your receiver. It's going to have nothing to do with what's coming in here. Now there will be a squelch function in the receiver here that turns off the output of this receiver when there's no input coming into the receiver. Repeater input and output frequencies are different. They must be, because we can't have crosstalk between the transmitter and the receiver. Now, not shown on this diagram are some very, very fancy filters. You'll usually see cylindrical filters used for 2 meters. They're big things, look kind of like air cylinders. They're a couple of feet high, maybe, and 6, 8, 10 inches in diameter. And there are probably several of them. Those are some cavity filters that are used because they give you very, very sharp bandwidth and very low loss. They are going to have to be in front of the repeater, and they separate the signal coming from, usually the same antenna is used for transmit and receive. Even if it's not, you've got to worry about the transmitter getting back into the receiver. And the function of those big filters is to simply keep the transmitter out of the receiver. The two are the receive frequency and transmit frequency are normally 600 kilohertz apart on 2 meters, going up to 5 megahertz apart on 70 centimeters. The further apart the transmit and receive frequencies are, the easier it is to filter the transmitter out of the received signal. But the more bandwidth you're tying up because of the pair of frequencies that are used in the repeater. Now, how do you know when you're listening to a signal and you hear a noisy signal? How do you know if the problem that's causing the noisy signal is caused by the RF path from this transmitter to your receiver, or from the sender's transmitter to the repeater receiver? Well, you got to listen to some cues that you can get, just some clues. You don't know just listening to a snippet of conversation. You don't know the answer to that. Could be either place that you're getting noise. What you can listen for is the local audio generated functions. As a minimum, this will be the CW identifier required by the FCC, and many repeaters will have other voice identifications too. Listen to those. If it's clean, yet the received signal you're hearing is scratchy, then it means that it's the path between the transmitter and this receiver, the guy transmitting and the repeater receiver, is causing the problem. If the local audio is also scratchy, then it's the transmitter to your receiver. So you have to work on this signal path to make it better. But if it's the other station to the repeater, and there's really nothing you can do about that. The other guy is going to have to figure out a way to get more signal to the repeater. He may or may not be having trouble hearing the repeater. He probably doesn't, because typically the repeater outputs are much higher than the output of your HT. HTs will run usually 1 to 5 watts out. Transmitters, 50 to a couple of 100 watts, something like that. Now remember, in FM, and usually not in sideband for other reasons, loudness of what you receive has nothing to do with the received RF signal strength. It has everything to do with the deviation of the signal. If the received signal strength drops too low, audio starts to sound scratchy and may break up. And whether that's through a repeater, you've got 2 paths to worry about, from the transmitter to the repeater and from the repeater to the receiver. And you have to deal with those separately. And that's just a repeat of what I just said. Now let's talk about one final subject, and I will shut up and quit bugging you. Electromagnetic radiation from your HT or any other radiator from that matter. We call it electromagnetic radiation for a reason. It has an electric component, the electric field, and a magnetic component, the magnetic field. Now, why do we have both of them? It comes out of the mathematics of a radiated signal. You can't have one without the other, just like love and marriage. They go together. If you have one, you've got the other. Electric field depends on the, well, both of them depend on the orientation of the antenna. And the electric field is going to be almost a straight line field if I were to plot it. Magnetic field is running circles around the antenna, but as I get far enough away from the transmit antenna, this looks like a plane wave too, because I'm just taking a very, very small snippet of the circle that defines the magnetic field, and it looks like a straight line to me. And the electric field looks like a straight line too, because it's I've just got a small snippet of that field. We talk about the polarization or the orientation of the RF signal, and that always is by custom is with relationship to the electric field, not the magnetic field. Remember, the two are going to look to you as two planes at right angles to each other. But when we talk about the polarization or the orientation of the field, we're always talking about the orientation of the electric field, not the magnetic. If the antenna is vertical, and you probably, and there's a reason I'm saying probably, you probably have vertical radiation, a vertical polarized signal you're radiating. If you turn the antenna so that it's horizontal, you're going to get horizontal polarization. Now, the repeater antenna at some high point is just about always vertical polarization for good and practical reasons for repeater use. This is not always true in amateur use, but it is true in repeater use. That the orientation of the antenna is vertical, so you have vertical polarization. You need ideally to match the polarization of your transmitted signal to the polarization of the receive antenna, and vice versa when you're listening to the repeater, which means that ideally you hold the antenna on your HT vertically at all times. If you hold it horizontally, you can lose a lot of signal. So try to hold it as much vertical as possible. And of course, in between, you're losing some signal, but how much depends on how much off. If you got good signal strength, you probably don't care. If you're marginal on signal strength and you got to have everything just so, then keep the antenna vertical. So that's kind of what I was saying here, but a little bit more information. If you got two HTs close together, well, guess what? They're going to have stronger signals to each other than the repeater signal, even though the repeater transmitter, it may be running a lot more power, maybe 10 times the power of your HT. If you got two HTs close enough together, then you're going to get more signal from the close-in HT, and that could cause problems when I've tried to listen to or record my signal on one receiver at my house, and I have a transmitter that is just barely enough power to get into the repeater. I can't hear the repeater at all because the signal I'm transmitting from the close by transmitter is overpowering the repeater signal, even though the repeater is higher and is putting out more power, but it's a lot further away. So that's the reason that it makes it hard sometimes to listen to your own signal coming back from the repeater because you just can't do it as a rule. Well, that's about all I have to say this morning. I appreciate your not figuratively throwing rotten tomatoes at me. If there are any questions, I will be happy to answer them. Otherwise, I turn it back over to the boss man.